Okay guys, we're back. Before we open a single plot, let's set expectation for what we should physically see so we know if the result is lying to us. A ball hit a plate. In the first few steps, nothing happens yet. The ball is just closing the gap. Then contact, and after that moment, kinetic energy should be drained out of the ball and internal energy should be building up in the plate, because that's literally what deformation is. Kinetic energy converting into stored elastic and plastic energy in the material. Then after that, the ball reverses. Some of that internal energy converts back into kinetic energy as the plate springs back and pushes the ball away. But not all of it, you see. So some energy stays behind as permanent deformation, some as damping. That's the physical expectation. A ball that bounces back with exactly the same kinetic energy it arrived with will mean a perfect elastic impact, which is not true for our simulation. It's not what we defined. So here will be some of the mental checklist we are going to look up for. The kinetic energy should drop as internal energy rises. Stress should peak somewhere around the moment of contact. Displacement should peak slightly after peak stress as the plate continues deflecting. If what we see on screen matches that story, then we are good. If it doesn't, then we know what we need to change upstream. Before we dive in, I want us to understand some quick terminologies. The von Mises stress isn't a stress in one direction. It is a scalar combination of all the stress components into a single number that predicts yielding in a ductile material. That's why it is the standard metric for impact problem on metal. It tells you in one value whether the material is approaching failure regardless of which direction the load is coming from. Now the second one, let's talk about the nodal displacement, which is how far a point on the mesh has physically moved from its original position. Now for the kinetic and the internal energies, these are the global bookkeeping of the whole simulation. If they don't conserve properly, none of the local stress numbers downstream can be fully trusted. Now let's move to the implementation. I'll go to File, and I'll go to Open, and I'll go to LS DYNA binary plot. That's what we are going to open. Now, if I go to my folder, what you can see here is that we have D3 plot, G3 plot 01, G3 plot 02. Now you're just going to select the G3 plot, the first one. Now from what we can see here, we are having exactly 11 steps. We defined 10 interval earlier, but you will see 11 here because state 0, the very first frame before anything happened, is counted. So there's no issue with this. We are just going to reorient the model. Let's reorient the model. Okay, this one is perfect. Okay. Now, let's animate this model first and see what's going on. This is our model here, and this is what is happening. Let's stop. Here's the slider that can help you to adjust the animation speed. Okay. Now, let's stop. And you can also click on animate here if you want it to go on again and again, a repeated loop. Now let's pull the actual result. You go to post. Here is post. Here you click on post, and you go to fringe components. You click on fringe component. This is what happens here. Now under the stress, we said we were going to select the von Mises stress. Here's the von Mises stress. Done. Now, let's animate our model back. Now, let's step through state by state. State 1, if we come here and let's stop and let's start at state 1. Here's step 1. You see, nothing happened at state 1. Let's come here. State 1, nothing happened. Now, when we go to next state, state 2, that's when the displacement happened. We are starting with the displacement. Let me just move this here real quick to ensure that we can see the effective stresses. Now, we are in step 2 and nothing happened in state 2. Let's move to state 3. This is when we have the first contact, and you see at the level of the effective stress here, there's already a variation, big variation. At each state, check the maximum stress reading, and let's say we move to state 4, it's increasing, 5, 6, 7, 8, and now let's say at state 8, let's stay at state 7. This might be the biggest. State 7. Let's take state 8. You see, now it means at state 7, this is the biggest deformation here, because when we go to state 8, the ball is starting back the reverse motion. Okay, so at state 7, you can see that we are already at 3.26 times 10 to the power 8. That's the maximum stress reading. Perfect. Let's reorient our model. Okay, let's try to look now at the displacement. And for that, we are still going to fringe components, and we are going to the NDV. Here, the NDV stand for the nodal displacement velocity. We go to the nodal displacement velocity, and we are going to select the result displacement. Done. Yeah, this is the result displacement. Let's animate it. And from here, you can see the resultant displacement, the maximum resultant displacement. Like I said, you can grab, increase, and decrease the speed. You can animate it as a loop, depending on what you want to see. I think our simulation is pretty cool for now. We are good. Now let's look at the energy. Stop this and move to the energy. And now for the energy, we are going to select the history. And if you remember in our previous episode, we were talking about the SK card. Now, this is what will give us the GeoStat data. And let's go to the global. This one is the GeoStat when I was talking about the global history of the simulation. When I was talking about the global history of the simulation, this is what I was talking about. And we are going to select the kinetic and the internal energy, and we are going to plot it. Now, this is what happens. As simple as that. Now, you can first move to the attribute to try and check which. We see that the internal energy is the green color and the kinetic energy is the red color. And everything is explained here and is good. Now, the kinetic energy starts at its maximum and is but normal because that's all the ball's velocity before impact. It drops sharply through the collision. Then as the ball starts the rebouncing, because this is the trajectory of the collision here. And now when the ball starts rebouncing, it climbs back slightly before settling. So that's just that. And now for the green curve, which is the internal energy, it's just the opposite story. It starts low, goes through the collision. That's it. It starts low, it goes through the collision, then ease off slightly as some of the energy converts back to kinetic energy during the rebound. This is when it is easing out slightly during the rebound, you see, and then levels out. So that's just a reverse story of the kinetic energy. So we are going to click done. I'm going to close it. Perfect. Now, one more view worth showing is the velocity vector. Now, if you want to, let's go to the velocity vector. First of all, we are going to click on this vector card. Click on the vector card, and we are going to select dynamic because you want it to be dynamic whole. We are going to apply. Perfect. Now, what happens here? Let's say done. No, let's click it back. Sorry. Apply. Now, if I animate this model, what's going to happen? Now you can see the different. Let's say I'll click on this part. Yes. Let's say area whole. Okay. Let's see. No, it's okay. Shell normal. Let's say I'll click on the velocity. Let's say click on the displacement. You see, you can just change the vector plot here and see what's going to happen. Shell normal, this is what happens. Okay, dynamic. So you can just click it and see what's going on. So that's just that. I'm going to apply, save. No, let me just click it done and you're good. You just keep it like that. Stop. That's the full loop, start to finish. We set the boundary condition and the contact. We configure the solver, we run it. And today we are actually reading the results, the stress, the displacement, and the energy balance. So that's just it. Thanks for watching and see you in the next lecture, guys.